Hello everyone, welcome back to the channel. Today we are doing Leetcode 38, count and say, which also happens to be the problem of the day for today. Let's have a look at what it says. The count and say sequence is a sequence of digit strings. So basically digits which are encoded as strings defined by the recursive formula. Count and say of 1 is equals to 1, and then count of say of n is the RLE, run length encoding of count and say of n minus 1. So for in order to solve any case which is greater than 1, you are dependent upon count and say of n minus 1. Therefore it's very clearly a recursive relation, right? And we know what RLE is. Simply it's a string compression algorithm. For example, if you have this string 33222251, so you're going to take this 33 and you're going to say that you have 2 times 3. That's why you're going to replace it with 2 3. You have 3 times 2, so you're going to replace 2 with 3 times 2, 3 2. Similarly, you have 1 time 5, so 1 5, and then you have 1 time 1, so 1 1. The question says, given a positive integer n, you need to return the nth element of the count and say sequence. So first of all, let's try to understand what that sequence is. Okay, it's very simple. If you're given n equals 4, then they're saying this is going to be the fourth element in the count and say sequence. How exactly? You see, count and say of 1 is equals to what? It's 1, because that is what they said. This is probably going to be our base case. If we solve this problem recursively, then this is going to be our base case. Then you see, for count and say 2, what do we need? We need RLE of count and say of 1. Are you getting it? What is 1? 1 is nothing but count and say of 1. So I calculate what count and say of 1 is, and then I return the RLE of that to count and say of 2. Count and say of 2 captures the RLE of 1, calculates it, becomes 1 1, and returns it to count and say of 3. What count and say of 3 does is it calculates the RLE of count and say of 2, comes out to be 21, and returns it to count and say of 4. Count and say of 4 catches the RLE of count and say of 3, calculates the RLE of that, and returns it as the final answer. Are you getting it? It's as simple as that. Let me do it one more time. Count and say of 1 is the base case. Now, count and I don't know how to solve the, or chalo, let's do it over here. Let's do it over here. Let's see. You know, how are we going to do this? Let me tell you. Recursion wants you to only understand one thing, and that is the flow of how it works. Okay, in order, you need to solve n equals 4, right? You're given n equals 4 and you need to calculate the answer for this. Let's understand how the flow is going to look like. Okay, now f is equals to 4 is what my final answer is, but I don't know how to solve it. So I'm going to rely on recursion, and I'm going to say, I don't know what the answer to this is. Just make the problem a bit smaller. Okay, just make the problem a bit smaller. So I reach f of 3. I still don't know how to solve f of 3, so I'll reach f of 2. I don't know how to solve f of 2, so I will reach f of 1. Now f of 1 is my base case. F of 1 is my base case, so what it's going to do is it's going to return 1. It's going to return 1 to whom? It's going to return 1 to f of 2. Okay, now when that happens, f of 2 receives 1, calculates the RLE of 1, and returns it to f of 3. The RLE of 1 is what? 1 times 1, so it's 1 1. F of 3 receives 1 1, calculates the RLE of 1 1, which comes out to be 2 1, and returns it to f of 4. F of 4 receives 2 1. Okay, calculates the RLE of 2 1, which comes out to be 1 times 2 and 1 times 1, and this is basically your final answer. Okay, again, if we were to do the same thing for f of 5, let's see how that would have worked. I don't know how to solve f of 5, so I will do f of 4. And you see, f of 4, the flow beneath f of 4 is something which I've already told you. So you know 100% that what is f of 4 going to return? F of 4 is 100% going to return 1 2 1 1. So I am going to utilize this. See, this is what recursion is. You don't know how to solve the bigger problem, but you rely on the smaller one. Okay. So I know 101% that f of 4 is going to return what? 1 2 1 1. Isn't it? That is something which we proved over here. Now, what is f of 5 going to do? F of 5 is going to capture, it's going to receive 1 2 1 1. It's going to calculate the RLE of that. How? 1 times 1, okay. 1 times 2, okay. And then 2 times 1. It's going to calculate this, and then it's going to return this as the final answer. So for example, if there was f of 6, it would have received this, calculated the RLE of this, and returned it. This is as simple as it gets. As simple as it gets. What happens is, apart from the base case, every state does only two things. It receives the number from the beneath state, and it returns the RLE of that. Returns the RLE of that. That's it. These are the only two things which you have to take care of in the recursion. Nothing other than this. See, so this is what the RLE is coming for the first 7 states, and you can very easily calculate that. And why am I showing this to you? Because the RLE function, we will have to make it ourselves, right? We'll have to make the RLE function by ourselves. So for example, if I take n equals 3, then how can I do it inside the code, right? This is, or maybe let's take n equals 4. Okay, a bit bigger problem. Now, I have 1 2 1 1. Okay, I will be standing at I, and I will capture whatever character I have currently. So it's 1. And what's the count of this character? The count of this character right now is also 1, because I have 1 times 1. Now when I increment my I noticed that the character got changed, because the last character which I was standing at was 1. So I will have a string answer. It's going to be empty initially. I'm going to push back inside of it two things. Number one, the count, which is 1, then the character, which is 1 in this scenario. So I have 1 times 1. Now I'm standing at 2. So my current character becomes 2. And how many times do I have 2? I have 1 times 2. Okay, let's see if I have it in the future as well. When I increment my I, what do I get? I get a change of character, isn't it? So that means I need to push back 1 times 2. I have 1 times 2, right? Okay, perfect. Now what's my current character? My current character is 1. 1. And how many times do I have 1? I have 1 times. Then when I increment my I still notice that I have the same character. So I'm going to increment the count. Okay, I'm going to increment the count. Then when I increment I, it goes out of bound. Goes out of bound, so basically tells me to stop processing. Then what do I need to push back inside of the answer? 2 times 1. 2 times 1. So this is exactly this. Okay, and try to dry run a couple of states by your own self as well, so that you understand how the RLE function is working, right? So having discussed this, let's now look at the code. RLE function is nothing but a very simple function. It receives a string, it gives you the RLE encoding of that, right? Perfect. So I have count and say of int of n, and what I'm doing is I'm utilizing recursion to solve the overall problem, right? So I have made a function solve over here, and inside of that function, the first thing which I'm going to do is write the base case, and that is something which the question provided to me, right? Count of say of 1 is 1. Then I need to make the recursive call. So what I'm saying is, forget about the bigger problem, solve the smaller problem first. Why? Because the recursion tells you this fundamental principle. If there's one thing which recursion tells you, it's that you forget about the bigger problem and you solve the smaller one first. Okay, so what I do is solve of n minus 1, and 100% you see solve of n minus 1, solve of n minus 1, 100% is going to return me a string. Just like f of 1 returned a string to f of 2, and f of 2 received this string, calculated the RLE, and then again in turn returned a string. I 100% know that there's going to be a string in this, smaller variable. Now from this state, what I'm going to do is I'm going to calculate the RLE of the string of the smaller problem and return it back to the state from which I came from. Okay, so exactly this thing is happening. F of 4, I say I don't know how to solve f of 4, please go to f of 3, please go to f of 2, and as soon as I reach f of 1, what do? I return 1. Okay, f of 2 captures this one inside of this smaller variable. Okay, now what does it do? It calculates the RLE of that smaller string and returns it to whom? F of 3. So it's going to calculate the RLE of 1, which is going to come out as 1 1, and it's going to return it to f of 3. Okay, f of 3 is going to calculate the RLE of 1 1, which is 2 1, and it's going to return that to f of 4, and then f of 4 basically returns the RLE of what? It returns the RLE of 1 1. Sorry, of 2 1. Okay, that makes sense. So this is as simple as it gets. If recursion is something which you think it's hard to understand, it's a bit complicated to understand, trust me, it's not. Okay, now the only thing which is left is for us to define the RLE function. So I make a function which is known as RLE. It receives a string and ultimately it's going to return an answer, right? I was talking about this thing. It basically answer is basically equals to the RLE encoding of whatever input string that you receive, this one, right? Now how am I going to do this? That's very interesting. First of all, I need to have a for loop, right? Just like I told you, this iteration, I'm using a for loop for that. Then I need to store the current character just like I did over here, and I need to store the current count as well, which is initially 1, right? Then what do I need to do? This is the most important part of all. You see, I do not have any condition over here for the for loop. I'm not, meaning I do have the condition, sorry, I'm not incrementing the I over here. I'm incrementing the I over here actually. And what you could do is actually you could do something like this as well. What I'm doing is I'm saying I plus plus is less than ftr dot size. You could do something like this as well. You could say ftr of I plus 1 is less than ftr dot size and do I plus plus over here. Okay, it's the same thing. It means the same thing. But just to let you know of an alternative way, I'm doing it like this, right? Perfect. Now, what this while loop is going to do is it's going to calculate the count of the current character. Okay, if it's going to calculate the count of the current character, then what do? First of all, that count is going to be an integer number, so I turn, using the toString built-in function, I turn it into a string. And then you see the frequency can be more than one, so it could be more than a single digit, right? It could be maybe 21 or even 200. So I need to make sure that this temp actually can be 200. So I need to push back each and every character which is there in the string. That is why I'm utilizing this for loop. And then once I have once I have pushed back the entire frequency, the count, I push back the character. And once I do it for all the characters which I have, once I do it for all of these, what do? I just simply return the answer. That's it. So if I submit this code, let's see if it passes all the test cases. It very clearly does. And one thing which I would give you as homework is try to think of the time and space complexity which we are using in this scenario. We are using recursion, right? Try to think of this time complexity and space complexity that we are using, and do mention it in the comments. And if you found, I hope you found this video helpful, and I'll see you the next time.